Hello, Assalamualaikum warahmatullahi wabarakatuh. We are Group C, and this video is about an assignment of laminar and parallel flow on a flat plate. Our group is consisting of 4 people, and all of us are from Section 2-3 BMKU. Here is our group member. The first member and the group leader is Irham Shamil, who is responsible for simulation and data analysis. Next is Nur Afika, which is responsible for video editing and making PowerPoint slides. The third member is Daniel Akil, responsible for voiceover and error correction. And finally, Pua, responsible for script writing and information gathering. In this assignment, we are required to use CFD software to analyze the 2D parallel and laminar flow of a flat plate. So, what is 2D flow? A 2D flow is a form of air or fluid flow where the flow velocity at every point is parallel to the fixed surface. The flow is mostly affected by velocity and can be solved using Blasius's equation. To use this solution, we have to assume that the velocity at any point on a given normal to that fixed plane should be constant. The theory: a solid surface will cause air to adhere to it as it passes by. The no-slip state is described by this phenomena, which is brought on by viscosity. According to this condition, the fluid's velocity at the solid surface is equal to the surface velocity. When this condition is met, a boundary layer with a relative velocity that varies from zero at the wall to a certain distance from the wall is created. The following image shows the boundary layer of a flat plate. The airflow is from the left to right of the plate. At the tip of the plate where the airflow meet, the airflow was initially laminar. As we travel across the length of the plate, the airflow becomes more turbulent and forms a turbulent region. The following is the objective or goal of our assignment. We need to find the variability of velocity over a flat plate using CFD simulation and to learn how to use a CFD software. The following is the geometry detail of the flat plate used in this simulation. In this simulation, we will create a 2D flat plate 1 meter in length and 0.5 in the height. The velocity of the air flow that will be tested is 1.5 millisecond meter per second and 2 meter per second respectively.
We first start by choosing fluid flow as our component. Right click on geometry and click new design model. Change the major grid spacing to 0.1 and minor step per major to 10 on setting. Draw a rectangle and put a dimension of 1 meter on vertical or V1 and 0.5 meter on horizontal or H2. Click on concept and click line from sketches. Click the drawing we just made and click apply on base object. Finally, we click on generate and we are finished on our geometry. Open up mesh window after closing the geometry window and generate mesh. This mesh is not detailed as we want, so we'll add more. Right click on mesh and add face meshing. Add one more mesh, which is sizing, and click on the top and bottom edge of geometry. Change the type to number of division and add 50 to number of division. Change the behavior to hard. The meshing is almost as we wanted, but we need to add a bit more. Add sizing on mesh and click the left side of our geometry. Change the number of division to 60 and behavior to hard. Choose the first bias type and enter 70 in bias factor. Then do the same thing on the right side, but make it reverse bias. Right click on our object and click create name selection. For the surface, it's airflow. For the left side, it's inlet. For the right side, it's outlet. Plate for the bottom, and any name for the top because it doesn't really matter. After done with meshing, we proceed with setup. Click double position for better outcome and press start. On model, change viscose to laminar and make sure everything is off. On material, press air and change density to 1 and viscosity to 1 E negative 4 or 1 times to 10 to the power of negative 4. On boundary condition, click on inlet and change velocity to 1.5 meter per second. On the far field pressure, change the type to symmetry. And the other doesn't need any changes. On method, change scheme to simple. Nothing to change on control. Click monitor and click on residual. Change all three absolute criteria to 1 times 10 to the power of negative 6. On initialization, choose inlet on compute from. On run calculation, make the iteration to a big number such as a million and click calculate. After it's finished run, this is the pressure control looks like. And this is how velocity contour looks like. We can also generate contour with more details in the result. After CFD post open, click contour and change location to symmetry 2 and variable to pressure to get pressure contour. We can also change the variable to velocity to get the velocity contour. We can also plot line graph in CFD post. To make line graph, click Insert, Location, and click Line. On point 1, change x to 0.5, and on point 2, change x to 0.5 and y to 1. The others remains 0. Click on chart icon and then change variable to velocity on x-axis and y on y-axis. On data series, the location is our previous line, which is line 1. Then click apply. We are going to add one more data from another analysis that used 2 meter per second as our air velocity. To do that, click add series. The location is changed to file and choose the CSV file from the 2 meter per second analysis. Then click apply.
This is the result of our simulation. Red color indicate higher velocity and vice versa for blue. According to this contour, it can be seen that the airflow is maximum away from the flat plate and decreases closer to the flat plate. This is because of the cohesion of air molecules on the flat plate shows down airflow and creates turbulence. Next, we plot out the graph of velocity against boundary layer height for two different velocity. According to this diagram, we can see that the velocity doesn't have much effect on the height of boundary layer. This is because the difference between 1.5 meter per second and 2 meter per second is too small for any changes on the boundary layer thickness. However, increasing velocity to, let's say, 50 meter per second would have a drastic effect on it. In conclusion, our analysis suggests that there is little to no difference is boundary layer thickness between velocity of 1.5 meter per second and 2 meter per second. This is due to the small difference between the two velocity. In this assignment, we have learned how to use CFD software and simulation effectively, and this knowledge will be very useful in the future. I want to thank all of my group members and our lecturer, Dr. Faisal, for supporting and guiding us. Thank you.